Evaluate the limit of a function by using the squeeze theorem. So in this lesson we're going to be talking about the squeeze theorem. It is sometimes also referred to as the sandwich theorem. And first let's just discuss why we would need the squeeze theorem. Well, so far we've looked at a couple types of graphs. The first type of graph, or the first type of function we look at, have been a very friendly function. For example, this is a continuous function, and continuous functions are friendly because, remember, we said the limits equal the function, i.e. the intended height will always be the actual height. And then next up we looked at a function, piecewise functions. That is a little bit, they're a little bit more difficult. However, they do behave in a way where we can determine whether or not the actual height equals the intended height. These piecewise functions allow us to evaluate all kinds of limits and figure out whether the two-sided limits or the one-sided limits exist. But then we have some functions that just really misbehave. And we've got these crazy type oscillating functions such as this one. And this one, it becomes a little bit tough to find the limit. Because with the first two graphs, we could kind of look at the graphs and we could determine the intended height. However, with this oscillating function, we keep oscillating our y values, going up and down, up and down, up and down. So this makes it a little bit more difficult to figure out the behavior of the function when it is oscillating up versus when it's oscillating down versus when it's actually approaching a singular point. So that's where the squeeze theorem comes into play. Alright, so before we can talk about the squeeze theorem, we have to talk about the process in mathematics known as squeezing. So to do that, we're going to look at a kind of real-world example here. So let's say we have three people, Ronnie, Percy, and Jasmine. Let's say Ronnie, Percy, and Jasmine all work at the same company. We know that Ronnie makes at least as much money as Percy. We know that Jasmine makes at least as much money as Ronnie. So by turning these two sentences into a mathematical sentence, we can come to the conclusion that Ronnie makes at least as much as Percy. So that means Ronnie will make more or equal to Percy. And then we know that Jasmine makes at least as much as Ronnie. So that's going to give us the compound inequality. Percy is less than or equal to Ronnie, who is less than or equal to Jasmine. Alright, so let's come in here and let's just, see and demonstrate how this compound inequality can work. So let's say that Jasmine earns $96. And let's say that Percy earns $82. Well, that means that Ronnie then is going to have a range for the amount of money that he makes. So we can figure out from this that Ronnie makes in between $82 and $96. And that's a range of $14. And that's great and all, but $14 is a lot. So if we want to figure out how much Ronnie makes, we need to pick better examples for Jasmine and Percy that's going to shrink that range of $14. So if we take a look at Jasmine, and that's not how you spell Jasmine. If we take a look at Jasmine, and let's say that one day she makes $90. And on that same day, let's say that Percy makes $86. So this is going to shrink because, based on our inequality, we know that Ronnie is going to make in between $86, and that's not 86, that's 66. Ronnie is going to make in between $86 and $90. But again, this is still a range. This is a range of $4, so there's no real way that we can determine how much Ronnie makes. But if we take a look at one more example, let's say that Jasmine makes $88 on one day, and Percy makes $88 on one day. That means that Ronnie, based on our compound inequality, has to make greater than or equal to $88 and less than or equal to $88. In this situation, he has to make more than and equal to 88 or less than and equal to 88. So therefore, in this particular situation, we know that Ronnie is going to make $88. And again, we were able to do this by starting out with our compound inequality, and we're able to look at different situations. So in our first situation, we had a range of $14 that Ronnie could make. In our second situation, we were able to kind of squeeze that range down a little bit to go from $14 to $4. And then finally, we were to squeeze a little more until we got the range of the inequality to be 0, meaning the lower bound is the same as the upper bound. And this is the process in math known as squeezing. So now, how does this actually relate to calculus, and how does this relate to limits? That's a great question. So let's say we have our crazy oscillating function here, and we want to find the limit as x approaches 0 of f of x. And as we can look at this graph, we can see that the function goes up and down, up and down, up and down, and doesn't appear to approach any number. So this would be a perfect case for the squeeze theorem. So first, let's just go ahead, and I'm going to outline the function in purple just to make it stand out a little bit more. Now, in order to evaluate this limit, we are going to want to squeeze this function. So we are going to want to do the same thing here that we did with Ronnie. Because remember, we squeezed Ronnie by what we knew about Jasmine and what we knew about Percy. So, in order to squeeze this function, we need to create that compound inequality. So we're going to start out with f of x. And to build this compound inequality, we first need to find a function that is always going to be less than f of x. So on the graph, we need to find a function that's always going to have y values that are less than all these purple values. In this case, we can choose g of x, which is just this particular upside down parabola. Then, for the upper side of f of x of our compound inequality, we need to choose a function that again has y values that are always greater than the purple y values, or a function that's always above f of x. And we can do that by choosing h of x, because as we can see here, h of x is a parabola with all the values above f of x. So now that we have this compound inequality, we can start looking at the limits. So we're trying to find the limit as x approaches 0 of f of x, which in order to do this means that we need to look at the limit as g of x approaches 0, and the limit as of h of x as x approaches 0. Now at the moment you can see that they are very far apart, because it looks like the limit of g of x is going to be at, what, I don't know, negative 0.25, and the limit of h of x is going to be at positive 0.025. So this is where the squeeze process comes in, because we're going to want to squeeze these together. So we'll squeeze once and they're closer. We'll squeeze twice and they're closer. We'll squeeze a third time until they are essentially on top of each other. So now they are on top of each other, and it looks like the limit of h of x and the limit of g of x are the same thing. It looks like they are both at the height of this particular L value. So therefore, we can say that the limit of g of x as x approaches 0 is equal to L. And we can say that the limit as h of x as x approaches 0 is also equal to L. And we know that the limit of f of x is trapped in between. So, just like with our example with Ronnie, Percy, and Jasmine, where we were able to squeeze Jasmine and Percy to kind of trap Ronnie in the middle, we were able to do that here. We were able to pick functions and kind of squeeze them together until we squeeze them between this particular L value. So, therefore, the limit as x approaches 0 of f of x has to be greater than L, has to be less than L, so therefore the only value that our limit can be is L. So that is essentially the squeeze theorem. We are trying to squeeze an upper and a lower limit till they get to the same value, and we squeeze the function we're looking for to find the limit of that function. All right, so now let's just kind of put this into words, a little mathematical lingo. So our conditions for the squeeze theorem are if g of x is less than or equal to f of x, and f of x is less than or equal to h of x, so if we have that compound inequality, and the limit of the lower function equals the limit of the upper function, in this case both L, then we have successfully squeezed our f of x function, and then we can conclude that since f has nowhere else to go, at the limit as x approaches a of f of x equals L. All right, so now we've kind of described how the squeeze theorem works, we've properly mathematically used the actual theorem to define the squeeze theorem. Next up, we're going to be talking about when can we use the squeeze theorem, or what conditions allow us to apply the squeeze theorem. So we're going to take a look at our first graph here. And here we have a oscillating function in the middle, that kind of light orange salmon color f of x. And we have an h of x that looks like a linear function that goes through the graph. And then we have a second function g of x, which is a linear function that also goes through the graph in the opposite direction. All right, so if we were to take the limit as x approaches 0 of h of x and g of x, we would see that these limits are equal. They both meet at the same point. There's an intersection point, so both their intended heights are equal. So one might think, okay, great. That means I can use the squeeze theorem here, and I can know what the limit of f of x is at 0. However, there's a problem. Because g of x is not always less than f of x. I mean, g of x is less than f of x for this piece down here, but up here, g of x is greater than f of x. So this side of the inequality isn't true. And same thing for the upper side. Here, h of x is greater, but this piece down here is less than. So since we can't form this compound inequality, the squeeze theorem does not apply. So we would not be able to squeeze these three particular functions together. Squeeze theorem would not work. All right, so here we have another example. We have our same salmon orange colored f of x graph in the middle, and here we have h of x is above f of x and g of x is below f of x. And we can see that no matter what, h of x is going to be greater, and no matter what, g of x is going to be below. So we could use this particular graph to form our compound inequality. That part of our conditions is satisfied. However, unfortunately, h of x and g of x, they don't appear to meet anywhere. So that means that their limits would not be the same value anywhere, which means the limit of g of x would not be the same as the limit of f of x, which sadly again means the squeeze theorem would not apply here. And taking a look at our last example, we are going to use h of x again, but this time it's lower on the graph, but h of x is still always above f of x, g of x is always below f of x, so our inequality works, and we can see that they both meet at x equals 0, so therefore the limit of g of x equals the limit of h of x at this point, which means the squeeze theorem does apply, and that means the limit as x approaches 0 of f of x will equal 0, and we are able to successfully squeeze that function. All right, so let's take a look at some examples and how this actually works algebraically as opposed to just graphically. So we're given the example, if we have a function, negative x squared minus 10x minus 20, is less than g of x, and then g of x is less than the function, x squared plus 10x plus 30, for all the x values in between negative 6 and negative 4, we're being asked to evaluate the limit as x approaches negative 5 of g of x. All right, so here we can see that we are trying to evaluate the limit of g of x around x equals negative 5. And we're given our lower function, and we're given our upper function. So since we're already given the inequality, this particular example is much easier because half the work is done for us. So I'm just going to recopy this inequality. So we're going to have negative x squared minus 10x minus 20 is less than or equal to g of x, which is less than or equal to x squared plus 10x plus 30. And now we're trying to evaluate the limit of g of x. But remember, with inequalities, what we do to one piece of the inequality, we have to do to all of them. So we'll take the limit of each piece of the inequality. So we'll take the limit as x approaches negative 5 of negative x squared minus 10x minus 20 is less than the limit as x approaches negative 5 of g of x, which is less than or equal to the limit as x approaches negative 5 of x squared plus 10, oops, that's not 10, that's 0. X squared plus 10x plus 30. All right, so thinking back to the squeeze theorem, our first condition is satisfied because we have a function that's always below and a function that's always above, and that condition was told to us in the problem. So this, our first condition of the squeeze theorem is true, it is satisfied, great. The next condition is that the limit of the lower function has to be the same as the limit of the upper function. So our next step is to evaluate the limits of the lower and upper function. Now these limits are polynomials, which means we can apply direct substitution. So when we do that, we're going to get negative, parentheses, negative 5 squared, minus 10 times negative 5 minus 20. And that's going to be less than or equal to the limit as x approaches negative 5 of g of x. And that's going to be less than or equal to, now for the upper limit we will apply direct substitution again, so I'll have negative 5 squared plus 10 times negative 5 plus 30. Alright, so now when we evaluate the lower expression and the upper expression, negative quantity negative 5 squared minus 10 times negative 5 minus 20 is going to give us a value of 5. And that's going to be less than or equal to the limit as x approaches negative 5 of g of x, which is less than or equal to. And then when we evaluate negative 5 squared plus 10 times negative 5 plus 30, we are going to get 5. And then here is where our second condition is met. We can see that the limit of the lower function is equal to the limit of the upper function. They are both equal to 5. So therefore, we have successfully squeezed the limit of g of x. So therefore, by the squeeze theorem, we know that the limit as x approaches negative 5 of g of x has to be 5 as well. And there you have it, our first example using the squeeze theorem. Alright, so for our next example, we're looking at the limit as x approaches 0 of x squared times sine of 1 over x. And we're being asked to evaluate this limit. Now, as you probably suspected, we're going to be applying the squeeze theorem to evaluate this limit. However, before we do that, let's just show why we need to use the squeeze theorem and why we just can't use direct substitution. So if we were to use direct substitution, we would substitute in 0, giving us 0 squared times sine of 1 over 0. Well, 0 squared is 0, and then sine of 1 over 0 is, well, that's where we run into the problem, because 1 over 0 is undefined. And how do we take sine of an undefined number? Because remember, sine represents the y value on the unit circle, and there's no undefined number on the unit circle. So that is the key giveaway, like ding, 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 ding. You might need to try the squeeze theorem. So we can just cancel that out because that's not going to work, and I got an extra cross cancel in there, so boop, boop, done. Alright, so we do want to use the squeeze theorem. So quickly, let's just review what our conditions are that we need to satisfy for the squeeze theorem. First condition is that we need to figure out, or we need to build our inequality. So we need a function that's always less than or equal to the function we're looking for, and a function that's always greater than or equal to the function we're looking for. And our second condition is that the limit of the lower function has to equal the limit of the upper function. So if we can satisfy those two conditions, we can apply the squeeze theorem and be on our way. However, they don't tell us what the g of x or the h of x value are. They don't tell us what our lower and upper functions are. And that is the challenge of problems like this, is we need to figure out what those g of x and h of x functions are. Now, we don't really just want to go in thin air and pull out these functions. We want to have a strategical approach. So we need a starting point, and from that starting point, we need to build our function. And whenever we're evaluating limits with trig functions, that gives us our starting point. And you might be saying, what are you talking about? Well, the key here is sine, because we know that the sine function is bounded. Based on pre-calculus, we know that sine has to be any number in between and including 1 and -1. And that goes back to the unit circle, because remember, the unit circle has a radius of 1, so that's what the greatest distance y can go is either up 1 or down 1. So sine is bounded. So this is our starting point. We're going to start with sine. And from there, we're going to eventually end up building our entire function. And when we build that entire function, that's going to give us the lower limit and the upper limit. So let's go ahead and start building. So I can rewrite -1 is less than or equal to sine of x is less than or equal to 1 as -1 is less than or equal to sine of 1 over x is less than or equal to 1. And you might be saying to yourself, wait a second, didn't you just do something to one part and you should have done it to all three? And while that's kind of true, it's kind of not, because I didn't really do something to just one part. I just rewrote the sine function. And by changing that, I didn't actually change the bounds. Now, what am I talking about? Well, remember we said sine of x is bounded by -1 and +1. And if we remember back to pre-calculus, when we change the inside of sine, that just affects the horizontal stretch or shrink of the sine function. It doesn't actually affect the range. It doesn't actually affect the output. So we can change the inside of trig functions without it actually changing the upper and lower bound. So that is fair game. However, this next part, I'm going to have to change all three pieces, because we can see that we already have the sine of 1 over x piece. We just need the x squared piece. So I need to multiply sine by x squared. But what we do to one piece, as we just went over, we have to do to all the pieces. So this is going to be negative x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. And there we go. We have our inequality. We have a function that's always going to be less than x squared times sine of 1 over x, and we have a function that's always going to be greater than x squared times sine of 1 over x. So our first condition is satisfied. Now next up, we just have to make sure the limit of the lower function equals the limit from the upper function. And we are trying to find the limit as x approaches 0. So we're just going to take the limit of each piece. So we're going to have the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of x squared sine of 1 over x is less than or equal to the limit as x approaches 0 of x squared. All right, from here I'm going to evaluate the limit all the way on the left, and I'm going to evaluate the limit all the way on the right. And for these, they're polynomials, so we can just use direct substitution. So the limit as x approaches 0 of negative x squared is going to be negative 0 squared, and that'll be less than or equal to the limit as x approaches 0 of x squared sine of 1 over x is less than or equal to, and then again x squared is a polynomial, so I can do direct substitution, so that becomes 0 squared. Well, 0 squared times a negative is just going to be 0, and then 0 squared is just going to be 0. So as we can see, we have now squeezed our limit as x approaches 0 of x squared times sine of 1 over x to have to be greater than 0, but also less than 0. So that means that we have just squeezed our function. So we have satisfied both conditions for the squeeze theorem. So therefore, by the squeeze theorem, we know that the limit as x approaches 0 of x squared times sine of 1 over x has to be 0. And there you have it. Boom! Done. Solved. All right, let's take a look at one last example, because this particular one, whoo, that looks confusing. Look at that. A quadratic expression times a trig function with a 1 over x minus 1. So we have a radical expression inside of a trig function. Oh my goodness! But it just looks difficult. With the squeeze theorem, we got this. So we're going to solve this just like the previous example. We first need to satisfy both the conditions. The first condition being that we have to find a function that is always less than or equal to our original function, and then a function that is always greater than or equal to our original function. Then we need to take the limit and show that the limit as x approaches a of our lower function is equal to the limit as x approaches a of our upper function. All right, so just like before, our first step is we need a starting point. So what can we start with? Well, fortunately again for us, we have a trig function, we have cosine. And based on our pre-calculus knowledge, hopefully remember that cosine of x is bounded by 1 and -1 for the same reasons that the sine is bounded. So therefore the output of cosine can at most be 1 and at least be -1. Well, our expression is in cosine of x is cosine of 1 over x minus 1, so we can rewrite it as that because, again, remember, changing the inside of a trig function doesn't affect its vertical shift and therefore doesn't affect the range. All right, so we've built the piece a little bit more. We now have this particular piece built, which means we're only missing the quadratic expression. And let's see, our cosine function is multiplied by that. So we can come in here and we can multiply everything by that quadratic expression, x squared plus x minus 2. And what we do to one piece, we need to do to them all. Which is going to leave us with negative the quantity x squared plus x minus 2 is less than or equal to the quantity x squared plus x minus 2 times cosine of 1 over x minus 1 is less than or equal to x squared plus x minus 2, and that's a bad squared. All right, so now we've successfully built our function, which has in turn given us our lower function and our upper function. So now we just need to come in and take the limit of both sides to make sure that our second condition is met. And I did meet the first condition, so let's make the check mark. All right, so now let's take the limits and see if the lower limit matches the upper limit. So we're going to have the limit as x approaches, what are we approaching? We are approaching 1 of negative the quantity x squared plus x minus 2 is less than or equal to the limit as x approaches 1 of x squared plus x minus 2 times cosine of 1 over x minus 1 is less than, woo, lots of writing, as x approaches 1 of x squared plus x minus 2. All right, let's shake the hand out a little bit there, let the Wi-Fi catch up with my writing. Whew, might get a hand cramp from all of this. Yay, upper level math. All right, so now we can evaluate the lower and upper limits. Remember, these two have to have the same intended height, or both these limits have to equal the same number in order for us to actually squeeze our middle limit here. And let's see, applying direct substitution, we're going to get negative, let's see, 1 squared plus 1 minus 2 is going to be less than or equal to the limit as x approaches 1 of the quantity x squared plus x minus 2 times cosine of 1 over x minus 1 is less than or equal to, and then direct substitution again is going to give us 1 squared plus 1 minus 2. All right, so now when we do evaluate the lower and the upper expressions, let's see, 1 squared plus 1 is 2, 2 minus 2 is 0. 0. Negative is just 0. That'll be less than or equal to the limit as x approaches 1 of x squared plus x minus 2 times cosine of 1 over x minus 1. And boy, is that a pain to have to write every time. Good thing we only have to write it one more time. And then evaluate the upper expression. 1 squared plus 1 is 2. 2 minus 2 is 0. So therefore, our lower and our upper limit are the same. So we have satisfied that condition, which means we can now squeeze it. So therefore, by the squeeze theorem, we can say that the limit as x approaches 1 of the quantity x squared plus x minus 2 times cosine of 1 over x minus 1 is equal to 0. And there we have it, squeeze theorem.